go ahead and look at the membrane of the neural lemma. On the membrane, we're going to have proteins that can pump ions. So this is moving ions against their concentration gradient. This does require cellular energy in the form of ATP. And you remember, we've already discussed the sodium-potassium pump. We also have some calcium pumps. Both of these require ATP to run, and both of them will move their respective ions against their concentration gradients and establish a concentration gradient across the membrane. We also have protein channels in the neural lemma. These protein channels will allow a specific type of ion to diffuse into or out of the cell. We've got leak channels that are always open, and we've got gated channels. And these gated channels can open and close just like a garden gate. Some of them are opened with chemicals, so these are called chemically gated channels, and some of them are opened with electricity, and these are referred to as voltage-gated channels. So let's look at sodium channels. Sodium channels specifically, in their resting state, are closed. Even though we've got a high concentration of sodium outside of the cell, because we've pumped it there, and the sodium would love to follow its concentration gradient and go into the cell until we reach equilibrium, that entry is prevented because the gate is closed. If we open the gate due to a voltage change, then sodium is allowed to move through the channel. So remember, the driving force of this ionic movement is going to be our concentration gradient, the differential in concentrations of sodium on each side of the membrane. But what allows it to move or allows it to diffuse is that open channel. If the channel is closed, then we don't have any diffusion. And then once the channel has been inactivated, then the gate is closed again. Sodium can no longer enter the cell. Sodium channels actually have two gates, so they can be in three different states, if you will. There's resting, there's activated, and then there's inactivated. Occasionally, in membranes of receptors in the peripheral nervous system, we'll have modality-gated channels. These are typically found in sensory neurons that respond to changes in the environment. For instance, we'll have some modality-gated channels that open in response to mechanical pressure. Do you remember that locker you had in junior high, where you would do the combination and the lock would stick and you would smash it with your fist and the lock would pop open? That's basically what these mechanically gated ion channels are. In their normal state, they're closed, but on mechanical deformation, they open up and then allow ions to flow down their concentration gradient. So when we look at the neural lemma of a neuron, we've got leak channels, we have sodium-potassium pumps, and we need to maintain our resting membrane potential. So you can see we've got our sodium-potassium pump, we've got sodium channels and potassium channels. Now the plasma membrane of our neuron has functional areas. There's the area that's called the receptive segment, which tends to be the dendrites and most of the cell body. There's an initial segment at the axon hillock, and then we have a conductive segment, which is going to be our axon and its branches, and then the transmissive segment is where we have our synaptic knobs that are producing our neurotransmitter. Each of these areas have specific channels in them. So as an example, here is our neuron. The entire membrane is going to have sodium-potassium pumps and sodium and potassium leak channels. The receptive segment is going to have chemically gated cation channels, just as we had on our neuromuscular junction. We also have chemically gated potassium channels and chemically gated chloride channels. The axon hillock, or the initial segment, has voltage-gated sodium channels and voltage-gated potassium channels. And the conductive segment also has voltage-gated sodium and voltage-gated potassium channels. And then down at the end, the transmissive segment has mostly voltage-gated calcium channels and calcium pumps.